We're now in section 5.5, and as you can see, we're going to be dealing with the real zeros of a polynomial function, and then we'll follow this up with section 5.6, where we talk about imaginary zeros. But we're going to discuss, as you can see in my goals today, the remainder and the factor theorems, the rational zeros theorem. All these are going to be useful tools in helping us find these real zeros, otherwise known as the solutions of a polynomial equation. And if it's in function form, we call them the zeros. But they're really synonymous terms. For functions, we find zeros, and for solutions, or for equations, we find solutions. So let's get right into today's lesson. So the remainder theorem works like this. We're going to be dividing this polynomial, this quartic polynomial, fourth degree, by this binomial x minus 2. And we have to remember the process called synthetic division. We learned this back in Algebra 2, but I realize it's been a while. So let me refresh your memory a little bit on how synthetic division works. The remainder theorem says that the remainder of this division process is also the output. Okay, so it looks like this. I'm going to divide. Actually, when you're thinking about the number that we put inside the house, I don't know if you remember this, but this little half box, there's a particular number that goes in here, and it will be the number that makes this binomial become 0. So in this case, that number is 2. So another way to remember this is you're always going to be putting the opposite number of the way it looks in the binomial. So if this had been plus 2, I would be putting negative 2. It's the number that makes 0 in this binomial. To the right of this, I'm going to list out the coefficients, 3, negative 6, but you got to pay attention to cases like this where you jump over an exponent. We jumped over the x squared term, so in that spot I'm going to have to plug in a 0 for the missing x squared. And then I keep on listing negative 5, and then I finish up with the constant, positive 10. So again, just pay attention, make sure you filled in any missing terms with a 0. So exponent 4, 3, there's exponent 2 missing, exponent 1, and constant. All right, come down, draw a line, and synthetic division begins by bringing down this first number, always. And then you multiply the number in the house times that number, so 3 times 2 is 6. And then you always add with synthetic division, so that's quite a bit different than regular division. Okay, and you just keep repeating that process. 0 times 2 is 0. Add those together. 0 times 2 is 0 again. Add those together. And then negative 5 times 2 is negative 10. And we add those together. So what the remainder theorem tells us is that when I input 2 into this function, I get a 0 output. Okay, and if you wanted to take the time to do it in old-fashioned substitution, where we just take the number and input it in for x, I won't take a lot of your time here, but I just want to make a connection. If you were to take your calculator and input 2 into all of this, you should get a 0 output. Okay? So this is another option for you to do inputs outputs whenever you're trying to graph these polynomial functions in the future, which we're not going to do that today, but I just wanted you to see this is an application of what is known as the remainder theorem. Well, the factor theorem is a follow-up to that, and it says this: if you do get a 0 remainder in this result, then this binomial x minus 2 is a factor. All right, so my final answer here, prove it with synthetic division, and then if you get a 0 remainder, you're going to say yes, x minus 2 is a factor of this particular polynomial, fourth degree. All right, so that would be the answer to that particular problem taken from your book. So let's try another one. Okay, let's see if x plus 4 is a factor of this polynomial. So I'm going to put -4 in the house. To the right of that, I'm going to list out 4. Notice I jumped over the x to the 5th, so I'm going to plug in 0, -64. There's no x to the 3rd, another 0. Coefficient 1, constant -15. Leave a space, draw a line, bring down the 4. 4 times -4 is -16. Add, multiply, add, multiply, add, multiply, add, multiply, and add. Okay, well, I did not get 0 as a remainder. So the output of -4 into this function would be -19, but since it's not 0, I'm going to say no, x plus 4 is not a factor. So for that block of problems where the instructions read like this, and you're doing the evens, I believe it's 12 to 20 even, this is your process. You're going to do synthetic division, see what the remainder is. Remainder 0, yes, that binomial is a factor. Anything other than 0, you're going to say no. Okay, now the maximum number of real zeros, you just have 3 of these. I believe it's 22, 29, and 31. So these are pretty simple. We have this fundamental theorem of algebra that basically says whatever the degree of the function is, that will tell you the maximum number of real zeros that are going to be possible. So pretty simple if you can understand how to find the degree, and that's just finding or identifying the highest exponent for the variable. And so for letter A, that would be 7. And so that's my answer. 7 is the maximum numbers. It's not telling me that there will be 7. It's just saying that at most there will be 7 possible. And there are other ways to determine how many there are exactly. And we're not going to get into Descartes' rule of signs, but that's one little tool. All we want to know is big picture, what's the possible number, maximum number of real zeros, and you don't have to actually find them. So basically just identify the degree. So for letter B, that's going to be 5, and you'll just zip through those 3 problems very quickly. Okay, so now let's talk about the rational zeros, how to find potential rational zeros. And this is the rational root theorem. Some people call the rational zeros theorem. And it works like this. The rational root theorem, I'll write that down for you. It says that to find all the potential rational zeros, or another word for roots, then we're going to make a fraction. And the fraction is going to look like this. The top of the fraction will be all of the factors of this last number, both the positives and the negatives. All right, so that's pretty simple. In this case, the factors of 1 are positive and -1. So list out the factors of the last number, and then below that, you're going to list out the factors of the very first number, the lead coefficient. So that's positive -1, positive -3. Okay, so rational root theorem says list out the factors of the constant, top part, then below that, the factors of the lead coefficient, and now come up with all the combinations of numbers that are possible from this. Okay, so one possibility would be 1 over 1, positive and negative, so that's obviously plus minus 1. But you could also have plus minus 1/3 as a possibility. And so, as it turns out, those are the only 4 possible rational zeros. Those are all rational numbers. And we're not saying that they are. We're just saying that these are possible. Before we even start attempting to find them, we know we're on the lookout. These are the ones that we're actually going to test in a future step. But at least it gives us a starting point of rational numbers that we look for as solutions. Okay. Here we go for letter B. So again, list out the factors of the last number. So that would be plus minus 1 divided by plus minus 2. And then below that, list out the factors of the very first number, plus minus 1, plus minus 2, and plus minus 4. And now just think about all the combinations of numbers that could be made out of this. Well, you got 1 over 1 plus minus. 2 over 2 is still 1, so we don't have to repeat that. Let's see, we have 2 over 1. See how we got 2 over 1 plus minus. And then we also have plus minus 1 over 2. We also have plus minus 1 over 4. And plus minus 2 over 4, but that's reduced to 1/2, so we already got that one. So just double check. It looks like we've got them all. 1, 2, 1 again, so you don't have to list them multiple times. 1/4, 2/4, which is 1/2. So you're just going to work your way through and make all the possible combinations to come up with the existing numbers in this fraction. And when you've listed all those out, you are done. So this would be my answer for letter B. All right. Now we're going to use the rational zeros theorem to help find all the real zeros. Okay, and that's what you're going to do in this block of problems. So once again, the rational zeros theorem, rational root theorem, also known as, list out all the factors of the last number, plus minus 1, plus minus 2, plus minus 3, plus minus 6, and then put that over the factors of the lead coefficient, which is 1. And so what these become are numbers that we're going to use in a test involving synthetic division. So probably saw this in Algebra 2. So what I'm going to do is I'm going to start testing these numbers one at a time. Okay. One thing that you'll need to do across the top is, just like we did with synthetic division, you're going to list the coefficients and the constant. And this really is synthetic division, but it's in a table format, so it looks a little different, but the process is still synthetic division. You're going to recognize it as soon as I run through an example here. So the 1 came from one of these. Okay, these are the possible numbers that you're going to test. You just list these down the side. If they don't come out of this, then don't list them. The only numbers that you list as possible rational zeros are from your rational root or rational zeros theorem. Okay, so with synthetic division, you bring down the first number and treat this is the number in the house. Okay, so you multiply. 1 times 1 is 1, and then you just add to the next number. So we set it up this way so we can do several different tests with just one table. Okay, so 1 plus 2 is 3. Multiply 3 times 1, that's 3, plus negative 5 is negative 2. Negative 2 multiplied, negative 2 times 1 is negative 2, plus negative 6 is negative 8. Well, the goal of this test is to get a zero remainder. Remember, we talked earlier how if I get a zero remainder, that tells me that, in this case, x minus 1 would have been a factor. Well, I didn't get a zero remainder, so 1 can't be one of the roots. All right, so I'm going to keep looking. So let's try positive 2. Bring down the 1. 1 times 2 is 2. 2 plus 2 is 4. 4 times 2 is 8. 8 plus negative 5 is 3. 3 times 2 is 6. 6 plus negative 6 is 0. We have a winner. One of our rational zeros, or rational roots, is going to be the number 2. Now I'm looking for a total of 3. Remember, the fundamental theorem of algebra says whatever the degree is, that tells you how many roots or solutions you're looking for. We'll say roots, or we'll say zeros for a function, roots for an equation. All right, so I know one of my answers is going to be the number 2. How do I get the other 2 answers? Well, these numbers represent a quadratic equation. 1x squared plus 4x plus 3 equals 0. And so once you get to quadratic level, you don't have to go through the table anymore. You can just go back and remember how we solve quadratic equations. And sometimes they factor. Sometimes you'll have to use the quadratic formula. In this case, factoring is possible because factors of 3 that add up to 4 are positive 3 and positive 1. And so I got my other 2 zeros. X is negative 3 and x is negative 1. And so we have found all 3 of the zeros. Just circle them like this when you find them. And we did it by using the rational zeros or rational root theorem. And this is what I want you to show when you do 46 to 56 even. Okay, so let's try another one of those. So once again, start off with your possible rational roots, plus minus 1, plus minus 2. And then below that, we're going to do plus minus 1, plus minus 2, and plus minus 4. So all of the possible numbers that come out of this is the rational root theorem, are going to be listed down the side of my table. And I don't want you to get the idea you have to test all of them. You just want to find the one that gives you a 0 remainder and then move on. Okay, so across the top, I'm going to do 4, 5. Notice my exponent's 4, 3, 2. So you just don't want to, if you jump over an exponent, make sure to plug in the missing 0, 10, and then 2. 4, 3, 2, 1 constant. Okay, so here's a little tip for you. If you notice in your function that all your signs are positive, there's this tool, I mentioned it earlier, called Descartes' rule of signs, and I'm not going to go into all of the details of that, but one of the things that this tells me is that I'm going to have negative roots. Okay, so if you see all positives, I'll save you, you can cut this list in half, you can just try the negatives. Okay, so let's try negative 1. Bring down the 4. Multiply negative 4 plus 5 is 1. Multiply negative 1 plus 9 is 8. Multiply negative 8 plus 10 is 2. Multiply again, negative 2 plus 2 is 0. So one of my rational roots is the number negative 1. So I've gotten now this equation, this function, down to 3rd degree. So until I get to 2nd degree, I'm going to have to use the table again. This time I'm going to use these numbers, 4, 1, 8, 2. And I'm just going to, once again, use the rational root theorem, but it's the same numbers. This time I'm going to test negative 2. All right, so bring down the 4. Negative 8 plus 1 is negative 7. 14 plus 8 is 22. I'm pretty pretty obvious that I'm not going to get a 0 remainder here, so I'm just going to move on to the next number. Let's try -4. -16 plus 1 is -15. 60 plus 8 is 68. That's not going to give me a 0 remainder, so it looks like that's going to be -1 again. This is kind of unusual. So let's try -1 again. -4 plus 1 is -3. 3 plus 8 is 11. And you can see now that we didn't get 0 for any of those. So, okay, so this is kind of interesting. I've exhausted what I might call the easier ones, the non-fractions. So now let's take a look at fractions like -1/2. So this is a good illustration. Sometimes you get to it very quickly. Other times you're going to have to work for it a little bit. So let's bring down the 4. 4 times -1/2 is -2, plus 1 is -1. This is +1/2 times 8, plus 8, sorry. +1/2 plus 8 is 8.5. Okay, and it looks like I'm not going to get a 0 there as well, so let's try -1/4. So let's see, this is -1 plus 1 is 0. 0 plus 8 is 8. 8 times -1/4 is -2 plus 2. We found it, and it turns out that it's -1/4. Okay, so I've got 2 down, and I've got 2 to go. All right, so I'm going to take these numbers, 4, 0, and 8. I'm now down to quadratic level. These numbers represent this equation, 4x squared plus 8 equals 0. Now the instructions were to find all of the real zeros. Notice that? Okay. Well, if you think about it, when I solve this, I'm going to do 4x squared equals -8, x squared equals -2, but this is not going to be a real 0 because when I do the square root of -2, I get the number I. So according to the instructions, I don't need these as part of my answers, these two. Even though I've got 4 total roots, 2 of them are going to be real and 2 of them are going to be imaginary, but it only wants the real solution, so that ends up being my final answer, -1 and -1/4. All right, so one more time, these are solving equations in the real number system, basically the same thing. You're going to follow the same process. So you can do the rational zeros theorem, +(-1) +(-2). That's the factors of the last number divided by the factors of the first number, +(-1) +(-3). And go through, look at all the possibilities that come out of this. And we're going to set up synthetic division. So 3, 4, -7, 2. Careful that you didn't jump over any missing exponents. 3, 2, 1, constant. Okay, and just start testing. You can start anywhere you want. 1 comes out of this, so bring down the 3. 3 times 1 is 3, plus 4 is 7. 7 plus -7 is 0. 0 plus 2 is 2. So that did not work, so let's try 2. All right, 2 you can see also comes out of this combination. So bring down to 3. 6 plus 4 is 10. 10 times 2 is 20, plus -7 is 13. That's not going to, I can already see that's not going to give me a 0 remainder, so we'll try something else, maybe -1. -3 plus 4 is 1. negative 1 plus negative 7 is negative 8. 8 plus 2 is not 0, so we'll try negative 2. Negative 6 plus 4 is negative 2. This is positive 4 plus negative 7 is negative 3. 6 plus 2 is 8, so that's not going to work. All right, so now we're left with some fractions, like we have positive and negative 1/3. Bring down the 3. So this would be 1 plus 4 is 5. This would be 5/3 plus negative 21/3 is negative 16/3. And this would be negative 16/3. Not going to give me 0, so let's try negative 1/3. Okay, so negative 1 plus 4 is 3. This would be negative 1 plus negative 7 is negative 8. And this would be 8/3 plus 6/3, which does not give me 0. So since I'm out of room down here, I'm just going to change these, and we'll test 2/3. Okay, bring down the 3. 2/3 times 3 is 2. 2 plus 4 is 6. This would be 12/3 or 4. 4 plus negative 7 is negative 3. This would be negative 2 or negative 6/3. Plus 2 is 0. So we found one of the 3. Okay. And now you take the numbers that remain, and you're at quadratic level, so you don't have to worry about using the table anymore. So this is going to be 3x squared plus 6x minus 3 equals 0. And I'm going to solve this by factoring, so just take out the 3. X squared plus 2x minus 1 equals 0. And solving the quadratic, there are no factors here that we could use, so I'm going to have to use the quadratic formula. So let's run through that very quickly, or you could complete the square if you prefer. I think that might be probably a little quicker. Let's just complete the square here. So I'm going to add 1 to both sides to set up the completing the square process. So I divided by 2, and now I'm going to be adding 1 to both sides, so that equals 2. X plus 1 equals plus minus the square root of 2. So the other solutions are negative 1 plus minus the square root of 2, and you'll just leave these answers in exact answer form. So I set out to find 3 solutions, roots, and here they are. 2/3, that's 1, and then this represents 2 because it's adding and subtracting. All right, so that gives you a taste of the rational root theorem, synthetic division. Some people call this the rational root test, and you got a good taste of how that works. So use the table till you get down to quadratic level, and then use one of your other methods, factoring, quadratic formula, or completing the square to solve from there. And that should take care of it. And these are the problems you're going to be doing in this assignment. And if you have any questions, let me know.